Welcome to The Explainer. Today we're going to talk about a technology that is totally revolutionizing how we get online. And it's not through some cable buried under the ocean. Nope, it's being beamed directly down to us from space. So let's just kick things off with a pretty surprising fact. When you think of the global internet, what comes to mind? Maybe you picture this, I don't know, a literal cloud of data just floating all around us. But that's not actually how it works. Not at all. In fact, for pretty much its entire history, the internet's been something way more physical, something you could actually touch. And because of that, it's also been a lot more fragile than you might think. Yeah, that's right. Get this. A staggering 99% of all international data. It travels through this massive network of physical fiber optic cables that are just sitting on the ocean floor. And that creates a hidden weakness, a very real one. So because we're so dependent on this physical infrastructure, right, the whole network is vulnerable to damage. But it also creates this huge bottleneck. It means that huge parts of the world are either completely unconnected or have terrible service. Okay, so for decades, we've had satellites up there for communication. We've used them for GPS, for satellite TV, all that stuff. But when it came to high-speed internet, they always had this one major unavoidable problem. We're talking about the classic geostationary satellites, or GEO for short. You know the ones, they're big, they're powerful, and they just kind of sit in one fixed spot relative to the Earth. That's actually great for something like broadcasting a TV signal. But for internet speed, oh man, their distance from us is a huge problem. And just how far are we talking here? Well, a traditional geosatellite orbits about 35,000 kilometers above us. To put that in perspective, that's almost 3 times the diameter of the Earth itself. It's way, way up there. So that immense distance, it creates a serious signal delay. We call it latency. And for a geosatellite, that delay is over 600 milliseconds. To you and me, that just feels like a painful, super frustrating lag. It makes stuff like online gaming or even a decent video call pretty much impossible. But now, there's a completely new approach that is just changing the entire game. The solution wasn't to build a more powerful satellite. No, it was a much more radical idea. What if we bring the satellites much, much closer to home? Okay, and what's so cool here is just how dramatic the difference is. Look at this. We go from 35,000 kilometers all the way down to just 500. And instead of just a few huge satellites, we're talking about thousands of smaller ones, all working together as a team, like a constellation. And just look at that latency. It just plummets. And this right here just perfectly shows what that means for you, the user. That 600 millisecond lag, that's what makes competitive online gaming or even a stable video call totally impossible. But 20 milliseconds? Wow, that's lightning fast. That's fast enough for things like remote surgery. It is a total game changer. So you see, this isn't just a simple improvement. It's not just a little bit faster. It is a fundamentally different way of thinking about global connectivity. It's an architecture that finally untethers us from those cables on the ocean floor. Okay, so what does all this new speed, this new architecture, what does it actually mean for the real world? Well, it means that for the first time ever, we can build an internet that truly, and I mean truly, covers the entire planet. Now, to make this happen, companies like Starlink are building what they call mega-constellations. And the scale of this is just staggering. It's a feat that's only really possible because of recent breakthroughs in reusable rockets, which brings the cost way down. Think about it. They're planning for nearly 10,000 active satellites in orbit by 2026. The sky is literally filling up. And look, this isn't some far-off theoretical future. It is happening right now. We're talking about bringing high-speed broadband to researchers in the middle of the Sahara Desert, to ships way out on the open ocean, to remote villages that have never had reliable internet access before. It's about finally bridging that digital divide. But as we launch thousands and thousands and thousands of these new satellites, filling up the sky right above our heads, it starts to raise some really serious and kind of complicated questions. The benefits are obvious, right? A globally connected world is amazing, but we really do have to stop and think about the potential consequences of this rapid, completely unprecedented expansion into low Earth orbit. On the one hand, you've got this incredible promise of universal connectivity. I mean, this could totally transform education, healthcare, economies for billions of people. It's a huge deal. But then, on the other hand, we're facing entirely new challenges. Challenges that could impact our planet and even our ability to get to space for generations to come. And that brings us to the crucial trade-off. See, these thousands of new satellites, they show up as little points of light in the night sky. That creates light pollution, and it can seriously mess with critical astronomical research. And at the same time, every single launch adds to the growing problem of space junk, turning low Earth orbit into a much more dangerous place. So you see, this isn't just a technical question anymore, is it? It's a much deeper question about the kind of future we really want to build. As we reach for the stars to connect everyone on Earth, we also have to decide, what kind of sky do we want to leave behind? It's a balance we're all going to have to figure out together.